Jnanam Paramam Dhyayam. Knowledge is supreme.
Today I will do what are called regular local rings. Before I formally start it, I want to give couple of motivations for studying this. So, for example, we have seen uh, if K is a field and we have a finite type algebra over K, then this corresponds to so called algebraic variety. Algebraic variety in K power n. So, we want to study this, and when one talks about variety, one it's equipped with the topology coming from a Zariski topology. So, one want to study points on this and especially the local behavior at the points. So, this local behavior at the points, if this V is the variety and A is the point there, then there is a corresponding, and if you call this as A, this A will correspond to the maximal ideal MA, and the local behavior of V at A, that will be determined by this localization, this local ring. This is called a local ring of V at A. So, especially one would like to know when is this point non-singular. Non-singular, this actually this concept more coming from the analysis. For example, if you remember what is inverse function theorem or implicit function theorem, so they correspond to these points, the differentials, the study of differentials of the differentiable maps and the functional matrix or Jacobian matrix and the rank of that matrix is involved. So, similar thing we want to do it for this, and as you can see now this depends on the coordinates here. So, one would like to have coordinate free approach. So, that is where I want to start more generally. So, now instead of varieties and finite type algebras and so on, we start with a Noetherian ring A. A is Noetherian ring. And then we have this spec. And here also there is a Zariski topology. Now, the points are not maximal ideals, the points are actually the prime ideals. So, and given P in given P prime ideal, we have this concept A localized at P. This is a local ring. And again the idea is by studying this local ring and its their various properties, one would like to get information about this P in a neighborhood that will not be globally, but in a particular neighborhood. So, that is what it is, and I want to prove at the end a Jacobian criterion. So, we will prove Jacobian criterion for regularity. This if not today, maybe next time. So, this will decide, this is the criterion which will decide when this local ring at P is regular or not. So, let us recall what we have proved so far. So, if you have a local ring A, so I will assume Now onwards the ring is local. So this is local. So there is only one maximal ideal, and sometimes we will say it's with residue field A by M. So it can be denoted by triplets A, M and A by M. So that's a local ring. And when I say local, we will we will assume that it is Noetherian also. And even more, sometimes when we want to assume more, then we will assume that this is a local ring of a finite type algebra over a field, just to get the feeling from the geometric feeling. Okay, so what we have proved is this is dimension of A. We have defined this dimension, it's a Krull dimension, and we have proved it is finite, and the three numbers, namely the degree of the Hilbert-Sample polynomial, Chevalier dimension and the Krull dimension, all these three numbers are equal. We know it is finite. And not only that, we have also proved on the way that this dimension is bounded by the minimal number of generators for the maximal ideal. This is the minimal number of generators for M, and this is well defined that any two minimal sets of generators for M, they have the same cardinality, and that cardinality is nothing but the vector space dimension of M by M square as a vector space over A by M. This is Nakayama lemma. So it can be strict inequality, but when it is equality, those rings are very important and they are called regular local rings. So that is the definition of regular local ring. So A is called regular. If Krull dimension of A equal to minimal number of generators for M, which is the vector space dimension of M by M square. Now also you can define if you have a prime ideal in general, we call, if the ring is not local, in non-local case, a ring is called regular, a ring is called regular if every localization A localized at P is regular. For every P in the spectrum. Now it's a big task. How do we test some given ring is a given local ring, whether is it regular or not regular? For example, if you want to test if you take the circle, coordinate ring of a circle, over real even, that is x square plus y square minus 1, is it regular? Okay, such questions we will address after acquiring some kind of basic properties of these rings. So getting back to the local situation, when we have a local ring AM, to study this, especially the dimension, if you notice, we have attached to this is associated gradating, GRMA. This is the direct sum, m power n plus 1, n is from 0. So, using this ring we have defined the Hilbert function and degree and so on. So, this is called associated graded ring. Of A. Okay. Now, the first important observation is, let us write it as a theorem, AM local then A is regular if and only if the associated graded ring is a polynomial algebra. D, where K is the residue field. Strictly speaking, I should say isomorphic as K algebras. And where this D is obviously, D has to be the dimension of the ring. Okay. So, proof. One thing I note here first, note that from the dimension theory we have proved one easy consequence is dimension of the ring, local case. This is the dimension of the GRMA. This I do not remember whether we have I have formally proved it, but in any case I want to discuss more about this in the tutorial sessions. So, this okay. So, once you note this, then this is easier, because we know that if the ring is regular, if A is regular, then we know the dimension of A is the minimal number of generators for M. That means, as a this GRMA as a algebra over A by M generated by homogeneous elements of degree 1, and they are precisely D in number. So, this is finite type K algebra generated by D elements of degree 1, because maximal ideal is generated by D elements. So, that means we have a natural surjective map from polynomial algebra in D variables to the associated graded ring. So, this Xi's will go to the generators of Mi's, mod, of course, these are mod M square, and this is surjective is clear because this is generated by these elements. So, this is a surjective K algebra homomorphism. Now, I want to claim it is isomorphism. It is kernel injective also. So, to see that if kernel is non-zero, if kernel is non-zero, then it will have at least one non-zero element, and this polynomial algebra over a field which is an integral domain. So, if kernel is non-zero and if I go mod that, this will be isomorphic to the, let us call kernel to be A. So, then we will get this isomorphism as a K algebras, but then the dimension of this will be equal to dimension of this, and the dimension of this would have dropped at least by 1, because A is a non-zero ideal, and we have seen when in integral domain, when you go mod the non-zero element, dimension will drop at least by 1, because the 0 ideal at the end will disappear from the chain. That will be a contradiction. So, this will mean that dimension D equal to, which is dimension of graded ring, which will be smaller, strictly smaller than D, which is absurd. This strictly small, this D is, but this is D. This D is the dimension of the polynomial ring, and if this A is a non-zero ideal, then this dimension would have dropped at least by 1. So, this is, but on the other hand dimension D, therefore, this is not possible, therefore, kernel is 0, therefore, it is an automorphism. So, that proves the associated graded ring is a polynomial algebra. Now, we have to see the converse. Conversely, so conversely assume that the A is the graded associated graded ring is isomorphic to the polynomial ring. So, we noted that the number of variables should be equal to the dimension D. If this, then this isomorphism is a graded isomorphism. So, this is a K algebra graded isomorphism. Graded means homogeneous, that means homogeneous elements of some degree will go to precisely homogeneous elements of the same degree. So, in particular the homogeneous component of degree 1, which is m by m square, and here homogeneous degree component of the homogeneous component of degree 1, which is precisely the vector space generated by a capital X1 to Xd. This is isomorphic to, this is the vector space, K vector space generated by these variables X1 to Xd. So, obviously, this vector space has dimension D. So, the dimension of this vector space, let us call it V, this dimension is D. Therefore, this dimension is D, as a K is A by M, but by Nakayama lemma this is precisely mu M, and this D was the dimension. So, we proved D equal to mu M. So, therefore, by definition A is regular. Yes, because you see this isomorphism is precisely xi going to the, we are this algebra, graded algebra, as a algebra over the zeroth component generated by degree 1 elements, and we are mapping the variables to the those generators. So, it is, and then extend it. So, it is homogeneous isomorphism. Okay. So, if you have finite type K algebra, that is I will denote it by K small x1 to small xn. So, this is quotient of the polynomial algebra modulus of ideal. And now if you take a prime ideal in this finite type K algebra P, that prime ideal first of all will correspond to a unique prime ideal in the polynomial ring which contains this ideal A. So, therefore, I will write, instead of writing a prime ideal in this, that is a prime ideal in the polynomial algebra, it is in the spec of Kx1 to xn and which contain A is contained in P. For such set also there is a notation VA. VA is a subset of all those prime ideals in the polynomial ring which contains A. So, if you take any such P, so P here, then, and if you let us call this ring as A, or let me call it R, then R localized at P is our A. A is R localized at P. So, in any case, in this case, the graded ring, the GRMA will look like polynomial algebra Kx1 to xn modulus of ideal B, and this is the graded algebra. This is K graded algebra. So, before I go on, I want to deduce. So, we will come to this case soon. So, I want to write one or two corollaries, corollary to above theorem, that every regular local ring is the integral domain. That follows from the fact that because if A is regular local, then we have seen this associated graded ring is a polynomial algebra. So, and associated graded ring is therefore integral domain, and if associated graded ring is integral domain, then the original ring is integral domain. That is easy to see. So, I will leave it for you to check this easy fact. If GRMA is a domain, then A is a domain. I will just say it orally, what we need to check. So, if we have given this is an integral domain, this is a graded integral domain. So, a graded algebra is a domain if and only if there is no homogeneous zero divisors. If you use this observation, then you can easily check A is a domain, because if A is a domain, then A times B is 0 for some A and B in the ring, and they are in the maximal ideal local ring. So, you choose a power of maximal ideal where A will belong, but not in the next power, and similarly for B. Then when you read the images of A and B in the associated graded ring, think of them as homogeneous elements of degree whatever the powers you have chosen, and complete the proof by using that. Okay, the second part. So, this is the part 1 of this corollary. Second part is regular local ring is, every regular local ring is normal. A is normal. So, we have seen in part 1 it is integral domain. So, when you say ring is normal, so it is a domain. So, normal means, so recall that normal means integrally closed in its quotient field, more generally total quotient ring. The total quotient ring is precisely this is, you take the minimal primes and take the union of that and then invert all of them. So, it becomes the, or other way to look at it is take the non-zero divisors and invert all of them. So, pass from A to S inverse A, where S is set of non-zero divisors. In A. So, this is this map will be then injective, and that is the maximum possibility, because we cannot afford to invert anybody other than non-zero divisor, because if you do, then this ring will become 0. So, this is injective, therefore, it makes sense to talk about integrally closedness of A in this ring, and if that happens, one calls the ring to be normal. But in this particular case, because it is a domain, this inverting all non-zero divisors means inverting all non-zero elements, that means this actually is the quotient field in this case. So, normal means A is integrally closed here, means every element of this S inverse A, which is integral over A, it must be in A. Typical example of normal domain is integers. The quotient field is Q here, and Z is integrally closed in Q, that is a famous observation by Gauss. And more generally, you do not need Z, but you have a UFD, A is a UFD. The same proof will tell you UFDs are normal in their quotient field. So, K is the quotient field of A, and this is normal. The same idea of this, the idea being used is the GCD, concept of GCD, concept of GCD, and then that was used by in this proof by Gauss. So, UFDs are normal, obviously. So, it is a big theorem that every regular local ring is a UFD, and that is what we are going to prove, but this proof involves homological algebra, and that is what I will prepare in the beginning, and the theorem at the end will be regular local rings are UFD, of course, but I am not using in this corollary. This corollary is simpler than this. So, how do you prove it? Again, the idea is the same. If you remember the assignment 1, that integral extensions, the supplements which I have written, there it was, you will see that if you want to prove A is normal, to prove A normal, enough to prove that the associated gradienting is normal. But if A is a regular local ring, then the associated graded ring is actually the polynomial algebra or a residue field. And again by theorem of Gauss, that polynomial algebra in several variables is a UFD. So, therefore, it is normal, and therefore, by that observation A is normal. So, one or two examples which you would have studied in earlier courses, let me mention few of them. So, for example, if you would have studied let us say A equal to this number rings which arise from number theory. So, Z adjoint root minus 3, for example, this is imaginary quadratic a ring of quadratic integers. So, this is in this case the maximal ideal is, and I am taking the maximal ideal. So, first this is not a local ring. So, let us take the ideal M, which is generated by 2 and 1 plus root 3, 1 plus minus root 3, this ideal. So, when I localize now, A localize at M, this is not normal, it is not integrally closed, because because just look at, I will give an element which is integral over this, but it is not there. So, first of all, let us take z equal to 1 plus root minus 3 divided by 2. This element will satisfy a polynomial like this, z square minus z plus 1 is 0. That you can check very easily, because when you square this, this is, so when you square this is 1 square, that is 1, minus 3 which is minus 2, and then minus 2 plus 2 root minus 3 and divided by this 4, this is z square, and minus z, that is minus 1 plus minus root 3 by 2. So, these 2 gets cancelled, this is 2 here, and then plus 1. So, this is with the plus sign, this is the minus sign. So, this term will get cancelled, and this is with minus minus half, this is half here, this is half there. So, that will get 0. So, therefore, z satisfy integral equation over this, but z is not there because these 2. So, this is not normal. So, therefore, in particular this ring is not regular. In particular, AM is not regular. One more observation, that in case of dimension 1, so remark, in case dimension of A is 1, we are get back to the case where A is local now, A local, and suppose the dimension of A is 1, then normality, normal domain and regular, these are the same. They are equivalent concepts.